Hello everyone, my name is Bankyrshan and I'm from Assam Don Bosco University. I'm from physics department. So the topic of of my lecture is based on hysteresis loop. So let's see what is this hysteresis. Actually, the word hysteresis is derived from Greek word hysterion, meaning to lag behind. Alright. So it was coined around 1890 by Sir James Alfred Dewey. So let's see what is this hysteresis? Actually, is the phenomenon of lagging of the magnetic inductions or the flux density behind the magnetizing force. Actually, this hysteresis it's mainly occur in a ferromatic substances. Why ferromatic substances? Actually, in a ferromatic substances, the irreversible phenomena is taking place. So by irreversible phenomenon is I mean that both magnetization and demagnetization is happening in a ferromatic substance. Alright, so the best example I can give you is of hysteresis. Why do we need to study this? So actually in a transformer, alright, this is a sketch diagram of transformer. In a transformer, when I hope you all experience some heat, alright, whenever you are near a transformer. This heat actually is due to the loss of energy. Okay, this loss of energy is it's due to what we call hysteresis. Okay, so actually what happening in the transformer, this continuation, the process of magnetization and demagnetization is taking place. All right, so let's see what is this hysteresis loop now. Okay, how it is obtained. Alright. Okay. What is this hysteresis loop? Hysteresis loop is actually the relationship between relations between the flux density and the external magnetic force. So now let's see how is this hysteresis loop generated. Okay, so as you see here, along x-axis H is the external magnetic field, and along y-axis it is magnetic inductions or the flux density. Okay, so now initially when H is 0, alright, when H is 0, B also is 0. Okay, so now when I increase H means that when I apply that external magnetic field in ferromatic substances, when I increase H, B increases in a nonlinear fashion, alright, until it reaches a point A. This point A is at the center. So now when I increase H, B, which is the flux density, increases along there. It increases in a nonlinear fashions until it reaches a saturation point. Saturation points mean that the ferromatic substances almost magnetized or fully magnetized. Alright, you see here the point is almost constant. Alright, so now when I decrease the external magnetic field, external magnetic field, it will reach point when H is 0 now. Alright. When I decrease mean when I demagnetize the ferromatic substances. When I demagnetize ferromatic substances until it reaches H is 0, B, which is the flux density here, is not 0. The value OC here is not 0. Actually here, what is happening in the substance experiences remanence. Alright, remanence. Okay, this remanence is actually it's the retentivity of a bar. By the word retentivity, I mean that the amount of the magnetization present in the ferromatic substances when the external magnetic field is being removed. Alright, so now here, okay, so now when I reverse the external magnetic field, minus H hertz, when I reverse the external magnetic field, now the flux density or the magnetic induction, which is 0. Alright, this value OD here, which make the flux density 0. The value OD here is actually the, so now the material here it experiences coercive force. Alright, coercive force. So on keep on decreasing or keep on demagnetizing the metals until it reaches a point E, where point E here is the saturation point. You see it's almost constant here. It's almost constant here, but in this case, the ferromagnnetic substances, it's almost or fully demagnetized, or the metals is demagnetized. Alright, so now from this, on continuing the process or on demagnetizing and magnetizing the material, we will obtain a complete loop, as you see. Alright, we will obtain a complete loop. Okay, this loop is what we call hysteresis loop. So now let's see why it is called hysteresis loop. Okay, it is called hysteresis loop as I mentioned earlier. According to the statement of hysteresis, it states that it is the phenomenon of lagging of the flux density behind the magnetizing force. Okay, so here now, as you see that when H is 0, B is 0. That's fine. So now when I keep on increasing, when I keep on increasing H, B increases in a nonlinear fashion. So now here, when I demagnetize a material until it reaches H to 0, when I reverse the external magnetic field to 0, B, which is the flux density here, the value OB here is not 0, which implies that B is not equal to 0. Okay, so now when I reverse the external magnetic field, now the value OD here, which make the flux density 0, so B here has reached 0. You see?
3.
So now I come to conclusion that B, which is the flux density, always lag behind H. You see, as H reaches 0, B has not reached 0, which means that the magnetic flux is lagging the magnetizing force. Okay, which matches with the statement of this hysteresis. So the zero value of B occur at the later of the zero value of H, which implies that the flux density is lagging behind the magnetizing force or the external magnetizing field. So this BH trace in which the loop is being generated is what we call hysteresis loop. So now let's see a few examples of hysteresis loop. Okay, now let's see the few examples of hysteresis loop. Okay, that's fine. So here, in case of silicon, all right, as you see that this area, the area of hysteresis loop here is quite small, which indicate that the hysteresis loss is also small. So for this reason, silicon steel, it is used for making a transformer core. All right. So now, in case of hard steel, as you see that this area, which is the area of hysteresis loop, is quite large. So the loss also is quite large. So for this reason, this hard steel is it's not used it's not suitable for constructing the electromagnetic magnet. So with this, the lecture of this topic of hysteresis loop is come to an end. So thank you.